Yes. Okay, so today we'll start, inshallah, this lecture, chapter 4, which is about the single equilibrium stage, and end of the chapter we will talk about flash calculations and how we're going to use the single equilibrium stage to do the flash calculations. I think similar to what you have in thermodynamics, but we will approach this kind of problems from mass transfer, or let's say separation point of view, inshallah. So what you're basically going to learn from this chapter is to understand the fundamental definition of the equilibrium stage, and why it may not be sufficient to achieve a desired separation. So we will talk about the equilibrium stage and the assumption that we use to assume equilibrium, and if it is not the case, which is in real life we don't have equilibrium stage, we have maybe 70% depending on the configuration of the stage itself. But we usually assume it is in equilibrium, and we do the calculation based on this assumption, but in reality there's no equilibrium at all in distillation. Okay, we'll go through that, inshallah, one by one. We explain the fundamental definition of equilibrium stage and how we're going to be able to use it to derive the equations. Since we are going to be dealing with separation design or separation equipment, sizing and design, we will be dealing with multi-phase all the time. We're going to have, as I mentioned earlier this morning, we're going to have maybe liquid and vapor or liquid and gas. So we will be dealing with multi-phase systems, and therefore we want to introduce you to the Gibbs-Duhem equation and how we extend this Gibbs equation or Gibbs equation to instead of only intensive properties, how can we use it for flow system when we have some not only intensive, but we have also extensive properties. We will explain that also as well. And how are we going to be able to use this Gibbs phase rule to determine the number of degrees of freedom? I think you already know what is the meaning of the degrees of freedom before, Ching 111. And now we will extend this to multi-phase systems. And determining this number, or determining the variables that we have to specify in any system to solve it is important. And it's very crucial. Before you can solve any problem, it's good that you know how many variants or how many parameters that you must specify to solve the problem. And the same definition of the number, that number. If it is 0, that means your problem is solvable. That means you have a unique solution. If the number is greater than 0 or less than 0, then you will have to adjust your input data, or you have to adjust your equations. We will see how we're going to generate the equations, or for each system, how many equations usually we have. And we have now more than one system, or more than one phase in our system, how we deal with that as well. Okay. So the second part is all about how we determine the number of independent, number of degrees of freedom. We will move to some other kind of terminologies used in distillation, widely used in distillation, and it is based on the TXY diagram and YX diagram. Very important to understand these. I think you already know that before in thermodynamics, but how are we going to be able to use these diagrams to solve flash calculation problems or separation problems? Of course, our concern will be to solve problems graphically. We will explain that also. And for that, we will need what's called Q line. We will explain what is a Q line, what is the effect of the feed condition on the Q line. Of course, for a single stage, now we're talking about one single stage, how we determine from the Q line and from the TYX or YX diagram, how we determine the composition of the outlet. So if you have, for example, stream, and then you have vapor and liquid at equilibrium, you need to determine, for example, Xi and Yi of your products. So usually this one is V, the vapor at the top, and this is liquid here, and this is your feed, and this is the composition of the feed. Usually using Z for the composition, mole fraction of the feed, and we use Y for the mole fraction of the vapor outlet. We use X as small fraction of the liquid product. Now we assume the vapor and the liquid are at equilibrium. And this is something we have to be careful when we solve problems in real life. And then we will talk about what's the meaning of isotrope. And isotrope, I think you already know that. There's phenomena that exist in some systems in which you have this mole fraction of the vapor and mole fraction of the liquid are equals, and therefore you cannot proceed or you cannot extend your separation beyond this point. So, and it's a very big problem, and it's naturally occurring problem. So it is not something that you have control over it, but you have to manage your system or to manage your separation to avoid this point. So it's good to investigate this phenomenon. You understand the different types of isotrope that can happen in your system and how to design your separation to avoid this point, the isotrope points. And we will see what is the effect of isotrope points in our separation. Okay. Of course, last thing, we will, I think, go through bubble point, dew point, and equilibrium flash conditions. I think the bubble point and the dew point calculations, it's already given in Ching, I think 212, I think thermodynamics course 2. But we will go through it again just to explain the idea. And as I said before, most of the topics that we're going to cover here are very much related to or are very much based on the course thermodynamics. Okay, so if you got any questions, please raise your hand or stop me at any time if you feel I'm a little bit fast here. Okay, don't feel shy because this is your okay. So this is these are the topics. So these are the things that you probably will learn from this chapter or from the contents of this chapter. But before we go to before we write the equation, Gibbs phase rule and the degrees of freedom, and what are the relationships between these two, we want to identify a little bit of basic definitions that we will use. So we have intensive properties, we have extensive properties, we have independent and dependent variables, and we have variance or number of degrees of freedom. So if I ask you this question, what is the intensive properties? Any idea?
Independent of the size.
Yes, that's right, exactly. Thank you very much. So it is something which is not a function of the quantity. Now, can you give me an example?
Temperature.
Good. Temperature is not function of the size. Any other? Pressure is what else? Since we are talking about separation, what else is you feel like it's very much related to this intensive property? Concentration. Concentration is not function. Sorry. Density is also not function of. Thank you. But what you said is 100% correct. Temperature is pressure, density, but more important is the composition. Exactly right. This is the term that you're going to be dealing with a lot because you are dealing with separation. So the composition is a very, very important factor that you will have around all the time. So composition can be expressed by how many factors or how many parameters?
Mass and mole.
Mole
volume.
fraction. So yeah, mole fraction is our preferred kind of parameter we use to express the composition, especially when we deal with separation. So we usually, especially when you have distillation, we usually deal with mole fraction. So mole fraction, if we are talking about mole fraction of vapor mixture, we usually use Y. And if we are using, or if we are, if we try to represent the mole fraction in liquid phase, we usually use X. Now this is the case in this course. Now we say Xi or Yi, we're referring to the component. So I is referring to the component. So I could be 2, 3, 4, anything. So it could be from I. This one I goes from 1 to number of component. A number of component, we usually want to stick to the abbreviations used here. So 1 to C. So C is going to represent the number of components you have in your system. Okay, so these are intensive properties: temperature, pressure, density, and mole fraction. Okay, what about extensive properties?
Depends on the size, mass and
Yeah,
volume.
so mass, volume, flow rate. So yes, mass, volume. So we call it flow rate. One example is flow rate. Now the flow rate could be in terms of volume, so we call it volumetric flow rate, or in terms of mass, or in terms of mole. So we have mole flow rate, mass flow rate, and so on. Now what about the independent and dependent variables? Or let's say equations. Not verbs. What is the dependent and independent equations?
The equations maybe that have intensive properties and
Okay. Now, I think from calculus you've learned that in order to have, now let me give you this example. Now if I say y plus x is equal to 2, can you solve this equation? Can you find the value of y and x?
we need another equation.
So we need another equation. Okay, can we say this one? Is this okay?
No, it is the same.
Why? So yeah,
We
the
can
same
solve
thing.
them together.
Okay, so that's the principle I want you to grab here, is that even you can have infinite number of equations, but all of them are independent, sorry, are dependent. So in order to solve an equation, when you are looking for, when you have, for example, two unknowns, in this case here, x and y, you need two equations, but we cannot just call them equations, we have to call them independent equations. So we have to have two unknowns, lemma x and y. So I need two independent equations. Now this one is not independent because this one is basically the multiplication of 2 by this one. And in this way you can have more than just two. You can have infinite number of equations. But if I give you another equation, I say y minus x is equal to 1, for example. Now this equation and these equations are two different equations. They are independent of each other. That equation 1 and equation 2 are not dependent on each other, and therefore we can use them because I need two equations, because I have two unknowns, y and x. Now I'm giving you this example to explain the independent and dependent principle. It's very important when you calculate or when you wanted to determine the degrees of freedom is to know how to identify whether this equation is independent or dependent equation. Then أحيانا you can find this very confusing in some more complicated problems. It's not easy sometimes to determine the number of equations that you can generate. Now, if I can take you back to, let's say, Ching 111, how many, what are the different sources that you can use to generate, for example, independent equations as a chemical engineer? What are the possible sources that can be used to generate an equation that are physically possible?
Like total mass equation.
Yes, thank you very much. Mass balance principle
Material
can be used. Sorry?
The material balance equations.
Yes. So the material balance is one that you can use. This is especially when you have in and out. So one of the sources that you will be using to generate your equations, it is going to be the material balance equations. Okay, what else? A very, yeah, and it's similar to the material balance, we have also energy balance. Yes, so we have energy balance, we can use it, and we have the material balance principles, and both says in is equal out, especially when you have steady state process. Now the extra piece of let's say information that you can use to generate, okay, momentum is good, of course, but momentum, as you probably already know from fluid mechanics, is usually used to, if you are looking for something related to the pressure gradient, or if you want to get the what about the ideal gas though? Is it? Ideal gas is not only the ideal gas, by the way. We don't call it ideal gas. We call these special relationship or physical. So you are right. The ideal gas is physical law. It comes under physical law. If you remember from Ching 1.1, we said we can have material balance, we can have physical law. Physical law is not only for the density, for any other stuff. And we have also constraint. If you remember, constraint. Constraints, it's very much related to the summation of y is equal all the time 1. Summation of the mole fraction is all equal to 1. Summation of x always equal to 1. And mole fraction in the liquid phase. Material balance, energy balance. Also, physical law, as you said, probably density is equal to mass per volume. This is physical law. But also density is equal to what? Pressure, molecular weight over RT. All these are physical laws. Okay? Average molecular weight and all other stuff. Okay, so and also we sometimes have what is called special relationships. Special relationships is also sometimes used, are also used, for example. But also we have what's called thermal equilibrium, because we assume it is equilibrium. We have, if we have here two phases, we have here the vapor and we have the liquid here, And we have here yi's, that means depending on how many components we have, and we have here xi. Now, as I said here, if this is going to be the pressure of the vapor and the temperature of the vapor, and here we have the pressure of the liquid and the temperature of the liquid, we said equilibrium relation it is related to, if you remember, Ki from thermodynamics is equal to Yi over Xi. Okay? Now, how many equations are we going to be able to generate from this principle? How many equations we can generate based on this equilibrium relations?
Depending on the number of species.
Thank you very much. So it will be function of how many components we have. It's very similar to the material balance. If you remember, material balance is also a function of the number of species you have. But now there is one condition here. I want you to understand this. Now, for material balance, we know if you have 4 components, that means you can generate 4 independent equations. But for the equilibrium relationships, you have to count only the components that are distributed between the 2 faces. If you have one component which is not distributed between the 2 faces, then you cannot count or you cannot use it. Now we have a lot of examples in which we have one component distributed between the 2 faces and one component is not distributed. Do you remember that from Ching 111? Can you give me an example of a case in which we have 2 components, but we don't, one of the components is not distributed between the faces? Can you give me an example?
The inert.
Inert, or yes, air. If you have, like, for example, air and liquid water, usually the quantity of air absorbed by the liquid phase, which is water in this case, is very small, to the level where we can safely say there is no any air in the water absorbed. But at the same time, we have water vapor and air. So, like, for example, if we have water here, let's say water here, so you will have air here plus H2O vapor. Of course, this is vapor, not the liquid. And here we have water. So now here we cannot say we have, in our system we have 2 components. If we assume air is going to be oxygen plus nitrogen. But in this relationship, we cannot write 2 relationships, simply because we will have to count only the components that are distributed between the 2 faces. So you have to be careful when you write the equilibrium relationship, or where you want to count the equilibrium relationships. Okay, good. Now the last thing, which is related to the variance or number of degrees of freedom, this is the number that we try to determine. Okay, so this is the number that we wanted to determine, and it will give me the number of parameters that I must specify in order to identify my system. Now, when we say identify the system, I think we mentioned that before in Xing 111 when we talked about the degrees of freedom in chapter 4. When we say we want to completely identify the system, means once we specify these parameters, we should be able to determine the flow rates and the composition of each stream in my system. But not always easy. You have to, sometimes you have to know how many parameters you have to specify in order to be able to specify or determine the rest. In other words, in mathematical words, how many variables you must specify in order to have number of unknowns equals the number of independent equations, regardless of how you're going to generate these equations. Okay, so the variance or the number of degrees of freedom is the number that we must specify in order to solve the problem. Now, in order to solve the problem, means in order to have number of unknowns equals number of equations. Clear?
Yes.
Good. So far so good. It's all okay. Okay. So now we have clarified all these terminologies that we will be using. Now we go to the phase rule. And as you can see, phase, that means we are dealing with multi-phase. We don't have only one phase, we have more than one phase. I think you already have this one before. And the general equation, without going into the way how it is being derived, it is the number of degrees of freedom is equal to the number of components minus the number of phases plus 2. Now there is a way how to derive it. Maybe we can discuss in the tutorial session, but at least I want you to understand how to apply it. So it's used to determine the number of variance, a number of independent intensive variables. Intensive, that means temperature, pressure, and composition, to be specified to describe the state of the system at equilibrium. So we are talking about the system which is at equilibrium, or the system that we assume it is going to be at equilibrium. Okay, so F is the number of independent variables that must be specified, C is the number of components, and B number of phases in the system. The same equation we used before in Ching 111. Okay, so let's see this system. Let's try with this system now. How we apply this one, and we assume we have 3 component system here. Now the degrees of freedom now calculated based on the phase rule says you have to count number of components minus number of phases plus 2. So now according to this one, how many degrees or how many parameters we have to specify here? Let me see here. Y2. Number of components is 3.
3.
Yes. So basically, if you go to this, you can say I have 3 components, as I mentioned here. You have 3. Number of phases 2, because you have vapor and liquid. So you have 2 phases plus 2. So that means you need to specify 3 parameters to be able to get the composition here and composition here. Okay? Cool. Now let's do it in the way how we used to do it before. So let's see if it is going to be okay if we do it as we used to have we used to determine the degrees of freedom. Now if I want to go there, so what I will, this is the equation here. So there's no need to mess up this one. So now independent intensive variables. How many intensive variables we have here? Can you count them for me?
2.
Just you have 3 components. So you have Y1, Y2,
8.
Y3. Okay, how many?
8.
Yes, 8. So we have 3 here, and we have X1, X2, X3. So 3 plus 3. Here we have 6 plus temperature and pressure. So we have 8 parameters. Now we want to, these are the unknowns. Let's say call them the unknowns. Now let's count how many independent equations that we can form here. Okay. So we have summation of y is equal 1. Summation of x is equal 1. So we have 2 here. We call them constants here. Summation of y is equal 1. Summation of x is equal 1 also. So these are 2 Equilibrium relations. How many equations we can form here? Equilibrium.
The K equation and
3. Because we have how many components? 3. So we have equilibrium equations for the system. We have K1 is equal to Y1 over X1. K2 is equal to Y2. X2, K3 is equal to Y3, X3. So we have 3. Okay. So now, as you already know before, degrees of freedom should be unknowns, lemma 8, minus the total number of independent equations that you can form. Now, if we count how many equations we have 3 plus 2. So this one is for this one, and this one is for this one. So that means you have 8 minus 5 is going to be 3. So both methods, or the two approaches, should give you the same answer. If you want to use the degrees of freedom, which is defined as the number of unknowns minus the number of independent equations, you get 3 palms, so you have to specify them. And if you wanted to use straight away the face rule, you will end up with the same answer. Is this clear? Good. So this is how we're going to use it when we have system which is at equilibrium. Now, but this is not our goal. This is just introduction. Our goal is to use this phase rule, or how to use the phase rule when we have continuous flow, like this system here. We have this system now, and this is the typical separation stage that you're going to design. So you will probably have your feed, you heat your system to some temperature, and then you wanted to separate vapor and liquid. And in order to do that, according to the phase rule, this is the derivation for the extension. So this one is not the same as the one that we already know here. You have a different equation. Why we have the different equation? Because this one is not a continuous flow. There is no continuous flow. This one represents the two phases at equilibrium. This one represents, or this one doesn't include, as you can see here, we don't have any flow rate. We don't have any extensive properties. We are dealing with mole fraction, temperature, and pressure only. Okay? So we are dealing with temperature, pressure, and composition. So we are dealing with intensive properties only. Now, but in cases in which we have some extensive properties, which is the common cases, or which is the real cases that you're going to deal with, is when we have flow rates. Now, flow rates, whether it's for the vapor or for the liquid, we have different formula, and that the formula says there is derivation also. We can discuss it together in the tutorial, but it's in your textbook here. You're not required to know how to derive it, but it's good you go through it and see what is the difference. It's basically using the same approach here in this the one that we usually have when we want to determine the degrees of freedom. So now again, we will determine the independent variable. Now we have to include both the extensive and the intensive properties. So we have here 1, 2, 3, 4. Q is also variable, 5, 6, 7, 8, 9, and depending on how many components we have. Now, if we wanted to assume we have 3-component system, we will have Z1, Z2, Z3, Y1, Y2, Y3, X1, X2, X3. Now, the difference from the previous one, we have to add the if VL, the extensive variables. Temperature and pressure also, which is this one. But also, since we have heating or cooling here is happening, we're going to have different temperature of the feed, so we have to add these also. And since we're doing some heating, so in our system there is also another variable called Q. So if you count these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So you have 17 variables. They are mixed between intensive and extensive variables. Now, what about the independent equations? We will follow the same approach. We have two constants. Okay, we have summation of x is equal 1, summation of y is equal 1. But my question is going to be, why don't we use summation of z is equal 1 as well? Is it possible to use it? Now I write here, constants are only 2, and I only say summation xi is equal to 1 and summation of yi is equal 1. But I didn't include summation of zi is equal 1. Should
No,
we
but
include it?
depends on the mole fraction.
Sorry, can you say it again?
Because it is the same as the xi, I think.
You mean Z? No, not necessarily. Z means Z1, Z2, Z3. Sorry?
Because we can relate them with the x and y.
Yes, very simple. Because it will become not independent, will become dependent equation. So yes, you have three constants, but the three constants, one of them is going to be avoided or must not be used. And the three, as your colleagues just mentioned now said, they are related to each other. You can prove that. You can prove that by writing the overall material balance equation and the material balance equation for each component. You can prove that this summation zi is equal 1 can be developed or can be generated using these two equations plus the material balance equation. Okay, since this is the case, we cannot include it. Yeah, it is equal to 1, but it is going to be taken into account by the other two constants, so you don't have to worry about it. Okay, of course it must be 1. Summation of zi is equal 1. It is something, how to say it, but it is guaranteed by these two constants. You don't have to add it here, since you have summation of y is equal 1, summation of x is equal 1, and you already have f is equal to v plus L. You can prove this one if you multiply this one by material balance equation. We have xi Assalamu alaikum. Sorry, I got disconnected, guys. This is technology, and we have to learn how to live with this one. Can you hear me now?
Yes, doctor.
Yes, doctor.
Sorry for disturbing, but this is. Let's go back to. I don't know where exactly I got disconnected. I was talking to myself. I don't know for how long, but let's get back because we don't have enough time. Okay, so that's what exactly where we stop here. Is that right? Do you see the screen, guys?
Yes.
Yes.
So we have, as I said, we have 17 parameters, or let's say mixed between intensive and extensive. These are extensive. This one is also intensive here, intensive, and the other one are intensives. We have two constraints, summation of x and summation of y equals 0. Equilibrium relationships, we have three, since we have three component system. We are dealing with three component system. Mass balance, we have also three component systems. So we have three equations that we can generate. The energy balance is regardless of how many components you have. Usually the energy balance will depend on the system. System will tell you whether you have energy balance equation or not. So either it is only one equation or there is no equation. So now once we got all of these right, all what you have to do is just say we have 17. These are the unknowns minus the number of equations, independent equations again. And as we can see here, we have 2, 5, 8, 9. So the number of parameters that you must specify is equal 8. So in order to solve this problem, you have to have 8 known values. Now usually we have 3, which is the composition, plus the temperature here 5, and you probably have this one and this one and this one. So from this you can determine the Q by energy balance, and you can determine the other composition of the vapor and the composition of the liquid based on the equilibrium relationship. So what you're going to do once you determine or once you specify the number of equations, the problem will become just as I mentioned before, it will become kind of iteration. You will use the proper method for iteration to solve your problem. Okay, and it will become more a numerical oriented problem than chemical engineering problem. Once you specify all the first stage is to specify the variables, and you specify the number of independent equations that you can have, and then you can specify from the difference between the variables you have and the equations you have. You can determine the degrees of freedom, or let's say the number of variants you must specify. Now, in this case, 8 will include both extensive and intensive properties as well. Okay, is this clear, guys?
Yes.
Yes, doctor.
Good.
Yes.
Yes, Nuran, Wissam, she's asking how we got F is equal C plus 5. This is, you know, when we have this one, when we said we have this equation here, you see we have the, no, this one here. Yes. The phase rule is defined as C minus P plus 2 when we have two phases at equilibrium. And when we have only intensive properties, only, now if we're going to have extensive properties as well, you will have to say F is equal to degrees of freedom is going to be C plus 5. So this is the difference. This one is used when we have extensive properties. Now, when we have extensive properties, when we have flow goes in, for example, F and V and L. Now, how we derive these two is not really important, to be honest. But if you are interested, we can go through it in the tutorial session instead of wasting your time, since you will not be required to derive this one in the exam. But personally, to be honest, I would love you to use the same approach I used here. This is the approach that you can use. Okay, you don't have to rely on this equation or in this equation. Use this approach. Then why I'm insisting to use this one? Then in some cases you have a little bit more complicated system in which that will not be a valid equation. So I personally never use this f is equal to c plus 5 or f is equal to p minus 2 plus c, that one. And whenever I need to determine the number of degrees of freedom, I usually use the traditional method, which is based on counting the number of variables, whether they are only extensive or intensive or mixed, and number of equations that I can generate. Now, the number of equations could be generated based on the mass balance, equilibrium relationship, and all other. This way, the way that I just explained here is going to be a little bit lengthy, but will be very accurate. And in this case, you will count each and every single independent equation that you can have. Then sometimes you get tricky questions in which you have three components, but not all of the three components will be distributed. And then in this case, that will not be a valid assumption. Then you might get the wrong answer because you assume something which is not the case. But when you break it down like I did here, then that will help you a lot. And this is the approach that is used by all the any chemical engineering industry or even in research. And doing this will not allow for any mistakes or allow for any missing information that might happen when you do f is equal c plus 5. The derivation, by the way, is there in your textbook with details, but I didn't find it to be very important to include it here, but at least I wanted to mention. But whenever you are asked to do it, please make sure you do it the way how I did it in the left side, which is by breaking down or by counting the number of variables minus the number of independent equations, and then that will give you the degrees of freedom. Now, as I said, we have energy balance, mass balance, equilibrium relationship. These are the ones that most likely you're going to utilize to generate your independent equations. Any other questions? So next time, we will start with this one. I give you example of how to apply this one. But as I said here, it is something very much related to physical chemistry. Here is how many degrees of freedom if you want to specify your system or define your system in this region or in this region or at this line or this line and so on. We will explain that and we will practice that inshallah next time, but give you a chance to go through the principle and the phase rule we just explained it this afternoon, inshallah. Any questions before we leave?
Doctor?
Doctor, can you upload the notes?
Yeah, inshallah, we'll upload them all in addition to the course syllabus, so you can keep track of the assessment activities and the breakdown of the course, inshallah. Just please remind me if I forget. Any other questions, guys?
Doctor?
Yes?
I have a friend, she's dropped the course by mistake when she was replacing the sections. Can you do anything for her or to add to her receipt? Nothing.
I don't have any control over the schedule or over the registered students.
Because both sections was full when she wanted to get back.
Maybe if you can talk to Dr. Ijaz, the timetable committee, maybe they can do something for her. But I don't have access. I don't have. I mean, maybe I can add her if I know the student number, but if she's not officially registered with me, and if it doesn't appear in the SIS system, then there's no point. End of the day, whatever she is going to, and even if she join us unofficially, then it's not going to be okay. Maybe you can ask her to go communicate with Dr. Jazz. Maybe he will help her.
Okay, thank you, doctor.
Okay, I got the question from one of your colleagues here, guys, too, regarding the number of members in each group. I think 7 is too much. I mean, too many people. 7, I think it's too many. I got the question from one of your students. 6 is going to be the maximum since we have only 30, I think, or around 30. So 6 is going to be 5 groups, will be good. Yeah. 4 is the minimum. I guess it's not going to be feasible for you. If you below 4, you are risking yourself at the end of the session. You will end up with only 2 members, and then will be not easy for you to finish your tasks. Okay. So 6 is the maximum, and 4, yes.
You prepare only from our section.
What do you mean prepare?
You prepare only from our section.
Yes, I prefer. Yeah, that would be good because last time we had problems trying to get the grades of the students who participated in the other sections, and again, Dr. Irfan was asking me for the grades of the students who participated in groups in my section. So it was a little bit صراحة يعني confusing.
Okay, thank you.
Okay, guys, see you inshallah on Wednesday. Wish you the rest of your day. Good luck, inshallah. Thank you very much.